What? Part 3 already? Heck yeah, part 3. So let's check this out. We're going to match each of the graphs below the situation which it fits best. In the place provided in the right, explain how you made your choice. I'm not probably going to write them out. I'm just going to talk them out because the job is for you to actually take that and transfer it so you can process it. And so you're going to explain how you know you're correct. So here's the deal. We have these 4 graphs, and they share something. In fact, if you look, they all seem to start at 5. You can look at the reading and determine that, but you can also just look at the graphs to determine that. They're all going to have a y-intercept value at 5. Okay? So that tells me that's not a way I'm going to change this around, but if I do look at these graphs, I notice 2 really important things. 2 of them are, if I can full screen this. Yeah, there we go. Let's go full screen. Okay. 2 of them are linear, so 1 and 3 are linear. These 2 and 4 are exponential, which is going to be important. And then the other thing is, if I look at the first 2, they're decreasing, last 2 are increasing. These are all good tools I have to help me figure out what's what. So there's 2 ways we can jump into this. We can look at them kind of one by one, decide where they go, or we can do a quick skimming and kind of decide right away if they're talking about a linear relationship or an exponential relationship. And here's the way to kind of determine that. If it's linear, what you're looking for is a constant growth. Like you're always gaining 6, or you're always gaining 9, or you're always gaining 12. When you're looking at an exponential relationship, you're looking for variable growth, meaning that I'm growing by like a percentage is a really kind of common way exponentials are told to people. Or I'm doubling or tripling, where it kind of implies I'm multiplying by change. So that's what I'm going to do first. I'm going to go through and just decide, are these linear or exponential? And that'll be kind of like my initial sort. And then I'll go through and then decide if it's increasing or decreasing. So let's check it out. The population of the city is 5 million, but it loses 20%. And that means it keeps only 80% of its population. Gee, these percentage numbers are big flashing red lights to tell me that this is exponential. Now, the other thing that I'm going to go ahead and do right now is that it's losing. So I know this is going to be exponential decay, which means it's probably this guy, but we'll determine that in a second. You put $5 in your bank account and get 20% added each year. Now, again, percentage, big flashing red light that it's going to be exponential, and the fact that it's being added means it's going to be increasing. Justin Bieber has 5 million Facebook friends. That should say 5 million, but 2 million unfriend him for every album he releases, which is probably true. But 5 million and 2 million unfriend him, so 2 million every single time indicates a constant. That means this guy is definitely linear, and since we're talking about it up here, if he's losing, that means it's decreasing. You plant a tree and it grows 2 inches per month. That's that constant growth I was talking about. 2 inches, 2 inches, 2 inches, 2 inches. So this guy is definitely linear, and since it's growing, it's going to be increasing. I think we did all the work that I think we need to do. This guy is exponential and decreasing, so this guy is here. You put 5, and we're looking for exponential and increasing, so that means it's this guy. Here we have linear decrease, so it's this guy. And then linear increase has to be this guy. So again, notice I didn't do any work. I didn't write any equations. I just have to kind of read the situation, make 2 quick determinations. Is it exponential or linear? Exponential usually being a multiplication or percentage. Linear usually being just like constant add or constant lose. Constant, 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 constant. And then the last thing I have to do is kind of differentiate, am I getting bigger, getting smaller, because these 2 are definitely getting bigger left to right, or I'm sorry, smaller left to right, and these 2 are definitely getting bigger left to right. So that's something to consider. Hey, so definitely a doable problem, you just have to kind of keep your head about you. Oh, these guys. Well, yeah, let's do these. I like these. We're just simplifying. These are easy. You guys totally know how to do this by now. It's just a big counting game. So we have a to the negative third. Well, the negative can't happen because it says no negative or no zeros. But we know how to deal with this. This negative tells us that we're in the wrong place. Meaning, if I put this guy over 1, these 3 A's just really belong on the bottom. So I got to flip those 3 A's to the bottom, and then we're good. That's all we got to do. 12 to the 0 power, that's simple. Anything to the 0 power is 1. Done. I don't care what it's to the 0 power of, it's 1. You know, you can say, here, I have this kitty cat, and it's to the 0 power. I'm like, it's 1. It's always 1, no matter what. Here's still something a little more complicated. We have different variables, different powers, but we're not going to freak out. What we're going to do is just combine our like terms. So here I have 4 A's. I take away 2 A's. I'm dealing with just 2 A's. Here I have negative 2b's, and then I add 10b's. That's going to be 8b's, and that's all there is to that. See how simple that was? Oh man, look at this crazy mess of a thing. Now the first thing I'm going to do is I notice I have some 0 powers here. So I'm going to eliminate those because those are just going to be times 1, which doesn't matter when everything else is multiplied. Now I'm going to collect some like terms. 5x's, 10 more x's, that's going to be 15x's. Negative 2y's plus 6y's should be 4y's. Bam! Okay, now this is going to get complicated because I have a whole bunch of stuff in parentheses. Then I have 3 parentheses. That's what that exponent means. I'm not going to, not going to freak out. I'm just going to stop and do some counting. So I have 2 4's. If I want 3 sets of 2 4's, that means I have 6 4's. Here I have negative 3x's. If I want 3 groups of negative 3x's, that means I have negative 9x's. Bam! And then if I have 2 y's, 3 groups of 2 y's should give me 6 y's. Now I'm not done because I have this negative, but it's okay. We know how to deal with a negative. It just means it's in the wrong place. So this guy in particular has to flip to the bottom. Now the 6 4's and the 6 y's do not because they're not negative exponents. These 9x's just belong in the bottom, and that's all we're going to do because I can't do anything else because everything's different bases. Now here's an example where the bases are the same, but not a big deal. Just kind of imagine 17 x's or 17 r's, across the top, and then 10 r's across the bottom, and I start canceling those r's out. 17 on top, 10 on bottom, 10 on bottom, kill 10 on top, leave me 7 r's on top. This is not too bad. Okay, so we have 3x's here, we have 5x's here. That leaves me with 8x's. 4x's on the bottom. Now I can still keep killing here because I have x's and x's. 4 on bottom, kill 4 on top, leave me 4. 64 to the 1/4 power. If I just knew a way to rewrite it, I do know a way to rewrite it because that is a power. The 4 itself is a root, which means I can write this as a 4th root of 64. Which literally means I need a number times a number times a number times a number to make 64. Now in this case, there is actually a nice whole number that makes this happen. The number you're looking for is like 2.8. So this is actually okay as it's set. So leave it just like this, okay? I might end up changing this tomorrow in class. I don't know. I talked to Miss Norton and Miss Ryan about it, but I'm okay with this being 64. I might have to change that number a little bit to make it a little bit different. 27 to 2/3. Again, we're not going to freak out about this guy either, and here's the reason why. That's still the power. That's still the root. So this just means that it's 27, the 3rd root of 27, and then I'm going to take that guy and then square it. Now this one is solvable, and here's the reason why. A number times itself 3 times, hence a 3rd root to make 27. Such a number exists. The 3rd root of 27 is actually just 3. 3 squared is 9, and that's the number I'm looking for this answer. The 3rd root of 125, that means a number times a number times a number to make 125. In this case, the number does exist. It's 5. So 5 is your answer, okay? So this concludes part 3. We'll see part 4 just in a second.